In this lesson, we are going to be looking at how constants can affect your expected value and your variances. So we're going to be looking at 6 different formulas, and I'm actually going to number them so that when I'm doing the notes, I can say, look back at equation 1, and you'll know which one I'm talking about. So the first equation that I'm going to number is this guy right here. This is going to be equation 1. So what this says is, if you are finding the expected value and you take your x's and you either add or subtract a constant to each of the x values, all that's simply going to do is take the actual expected value and add that same constant to the average. So if you change all of the data values, you're changing the expected value by the same amount. Variance, however, if you take your x's and you add or subtract a constant to each number, variance doesn't change. So this is equation 2. Adding or subtracting to the x values doesn't change variance at all. It just stays the original variance. So adding and subtracting only affects expected value, not variance. Now, what happens if we multiply? This is equation 3. If you take each x value and you multiply it by a number, then you simply take the expected value and you multiply it by that same answer. Pretty logical. Variance, this is equation 4. If you take each x value and you multiply it by some number, variance actually gets much larger. You're going to take the variance and not multiply it by a, but you're actually going to multiply it by a squared. So it's going to get even larger than expected value. So adding, you add it to expected value, you do nothing to variance. Multiplying, you multiply to expected value, and you multiply by the squared constant with variance. Now what happens if we combine two variables altogether? Two totally different variables. So if you are adding or subtracting two different variables, you simply add or subtract their two expected values. Pretty simple. This is going to be equation number 5. And our last equation, equation number 6, if you add or subtract two variables, variance, the big difference is variance is only addition. Whether you're adding or subtracting doesn't matter, it's always addition. So let's take a look at some of these equations, and we're going to start with just using straightforward data that I give you. Okay, so for this example, I am giving you some data over here on the right side in this little table. I'm telling you the mean, which is another name for expected value, so this is EX, for X and Y, and I'm also telling you the standard deviation for X and Y. And you are being asked to find the mean and the standard deviation for some new problems. Well, one thing that we need to realize first, if you think back at all 6 of the formulas we just looked at, standard deviation wasn't mentioned anywhere. We need to know, so I'm going to add in a column here, we need to know the variance for X and Y. Well, if you remember from our previous lesson, if we know variance, we square root the variance to find standard deviation. And so if we're going the other direction, what's the opposite of square rooting? Well, that's squaring. So the variance is going to be whatever the standard deviation is squared. So 12 squared is 144, and 3 squared is 9. So now we have all of our data that we need. This first problem, we're taking our x and we're subtracting 20. So we need to find the expected value of x, take away 20. Well, if you look back at your previous page of notes, this looks exactly like example or equation 1. So I'm going to rewrite it the same way it's rewritten in equation 1. I'm going to take the expected value and I'm simply going to subtract 20 from that answer. Since I was subtracting from x, I'm subtracting from the expected value. So what's the expected value of x? Well, if we come over in our table, that was just another name again for mean. So we're using that 80 there. So we're going to take 80 minus 20 and we get 60. And that's all there is to using that formula. We're going to do the same thing with variance. Variance of x minus 20. Okay, so the variance with subtraction is equation 2. If you look back at your previous slide, equation 2, when we add or subtract a constant, the variance doesn't change. So it stays exactly the same. So the variance, make sure you're looking at the right column, we're over here on variance, is 144. And we're done. But we need to find one last thing, the standard deviation of x minus 20. And if you remember, that's simply found by square rooting the variance. And the square root of 144 is 12. So that's how we do those problems. That's not too bad. It's just using the formulas. So let's use the formulas for this next one. We're trying to find the expected value of 0.5 times y. Notice we're changing letters. Okay, well, which formula should we reference? Look back to the previous slide. Expected value and multiplication is equation 3. So if we rewrite it, we're just going to keep the a value times the expected value of, whoops, let me make sure I have the right letter there, the expected value of y. So we're going to keep the 0.5 and we're simply going to multiply it times the expected value of y, which is 12, and 0.5 times 12 is 6. Okay, well, let's do the variance now. The variance of 0.5y, so look over at equation 4. We need to take a squared, so 0.5 squared times the variance of y. So I'm going to keep the 0.5 squared, and I'm going to multiply it by the variance of y, which is 9. So 0.5 squared times 9 comes out to be 2.25. Now, we only did that because we need to know the standard deviation of 0.5y. And so we need to square root 2.25. And if we square root 2.25, we get 1.5. So far, hopefully those equations don't seem too bad. We're not done with this example, though. We're going to go over to the next slide, and we're going to look at part C. Now we're mixing the two letters together. So this is where we're going to use equations 5 and 6. So we're going to find the expected value of x plus y. Well, if you look back at equation 5, when you add x and y, you simply take the expected value of x plus the expected value of y. Well, look back at your table. The expected value of x is 80. Remember, that's mean. Plus, the expected value of y is 12 for a total of 92. Let's do the same thing with variance. Variance of x plus y. So look at equation 6. With variance, if you remember, it doesn't matter whether we are adding or subtracting. Variance is always addition. So it's variance of x plus the variance of y. Well, look at your data table. The variance of x is 144 plus the variance of y is 9 for a total of 153. But we need the standard deviation of x plus y. So I just need to square root 153. And I get, and yes, you may round to one decimal, 12.4. All right, well, that was easy. So far, hopefully you're thinking, well, these equations aren't bad at all to use. So let's look at we're changing one thing. Now it's x minus y. So the expected value of x minus y, go back to equation 5. If it's minus between x and y, it's minus between their expected values. And yes, that's supposed to be a y. So the expected value of x was 80, but this time we are subtracting the expected value of y, so we're subtracting 12, and that leaves us with 68. Variance of x minus y. Look at equation 6. Remember, variance is always addition. So we're still going to take the variance of x and add the variance of y. So this is actually the exact same answer as the previous part. So 144 plus 9 is 153. And that also means that the standard deviation of x minus y is also the exact same answer, which is the square root of 153, which was 12.4. So far you should be thinking this isn't too bad. Now, this last example, you see some subscripts there. Do you notice it says y sub 1 and y sub 2? All it really means is we're just going to use the letter y 2 times. We're just going to do the expected value of y plus y. Well, with addition and expected value, we're looking at equation 5. And so adding stays adding. So we're doing the expected value of y plus the expected value of y. So look back at your data table. The expected value for y was 12. So 12 plus 12 is 24. And we're going to do the variance of y plus y. If you remember, variance with equation 6 is always addition. So variance of y plus the variance of y. Well, the variance for y, if you look back at your data table, is 9. So 9 plus 9 is 18. And we found that because we need the standard deviation of y plus y. And the square root of 18, rounded, is 4.2. So we're going to do one more, and maybe we'll do some of the more challenging parts to it. So exact same stuff, exact same data table. So I'm going to go ahead and extend my little lines here and add back in my variance. My numbers are still 144 and 9. So nothing's changed. I'm just making the equations a little more challenging, not much. So this is, if you notice, this first one is mixing two equations together. So we're going to find the expected value of 2y plus 20. Well, let's focus on the 2y part first. If that 20 wasn't there, then this would look like equation 3. And equation 3 says we simply take 2 times the expected value of y. Well, let's look at the other flip side. If that 2 wasn't there, and it was just y plus 20. Well, y plus 20 is equation 1. And equation 1 says it's the expected value plus the constant. So all we're doing is mixing the two together. So we're going to take 2 times the expected value of y, which is 12, plus 20. Well, 2 times 12 is 24, and 24 plus 20 is 44. So it's just mixing the two. Do the same concept with variance of 2y plus 20. So again, we're going to pretend that 20 isn't there. If the 20 is not there, then we're looking at equation 4. And equation 4 says whatever we're multiplying by, which is 2, we're going to square it, and we're going to multiply it times the variance of y. Now, if the 2 wasn't there, and it was just y plus 20 is equation 2, and equation 2, if you remember, the plus number, the plus 20, cancels out. So we're not using the 20. So it stays 2 squared times the variance of y. So we're going to do 2 squared times, and the variance of y is 9. 2 squared is 4, and 4 times 9 is 36. And finally, we need the standard deviation of 2y plus 20, and the square root of 36, hopefully everybody knows, is 6. Okay, so we've already done one with multiplying. So you know what? We'll do this one real quick. The expected value of 3x. If you look back at equation 3, we're going to do 3 times the expected value of x. So 3 times 80 is 240. The variance of 3x, if you look at equation 4, for the variance, we're going to keep 3 squared times the variance of x. 3 squared, the variance of x is 144. This is a big number. 3 squared times 144 is 1296. Finally, the standard deviation of 3x, the square root of 1296 is 36. And let's keep going. We have 3 more parts. All right. So again, we're mixing in some numbers with 2 different letters now. So let's look first at the expected value of 0.25x plus y. So we're going to break this one down the way we did the last one. Let's pretend that the y is not there. If it's just 0.25x, then that would be equation 3. And equation 3 says that it will be 0.25 times the expected value of x. Now let's pretend the 0.25 isn't there. If it's just x plus y, then that's equation 5. And that says we add the 2 expected values. So we're just mixing the 2 concepts. So we're going to take 0.25, make that a little heavier, times the expected value of x, which is 80, plus the expected value of y, which is 12, for a final answer of 32. We're going to do the same thing with variance. The variance of 0.25 x plus y. Again, pretend that the y is not there. If it's just 0.25x, it's equation number 4, which means it's 0.25 squared times the variance of x. And if the 0.25 isn't there, x plus y with variance, equation 6, always adding. So we're going to take 0.25 squared times the variance of x was 144 plus the variance of y, which was 9, and we get a total of 18. And so I'm just using that to find my standard deviation. So I need to square root 18, which decimal is 4.2. So this next one is just throwing subtraction with it. So we're going to do the expected value of x minus 5y. So this time we're going to pretend the 5 isn't there for a second. If it's just x minus y, then it's the expected value of x minus the expected value of y. That's per equation 5. If the x isn't there and it's just 5y, then it will be 5 times the expected value of y. We're just separating. It's kind of like we distribute the e kind of. The expected value of x is 80 minus 5 times the expected value of y is 12. 80 minus 5 times 12 comes out to be 20. Now, variance of x minus 5y. Again, pretend the 5 isn't there. If you remember, with variance and equation 6, variance is always adding. So we're going to do the variance of x plus the variance of y. Then, if we ignore the x and we only focus on the 5y, if you go back to equation 4, we need to insert a little 5 squared before the variance. So the variance of x is 144 plus 5 squared times the variance of y, which is 9. And this also comes out to be a pretty good size number, 369. And we use that because we need to find the standard deviation. If we square root 369, we get 19.2. All right, last one on this particular slide. When they have the subscripts, remember, the subscripts don't mean anything. It's just the expected value of x plus x plus x. Well, equation 5 says that if we're adding the x's, we're adding the expected values. So it's e of x plus e of x plus e of x. All three the same letter, all three the same answers. So it's 80 and 80 and 80, which is 240. Then we're going to do the same exact thing with variance. Variance is always addition because of example 6. So that's variance of x plus variance of x plus variance of x. The variance for x was 144 plus 144 plus 144, which comes out to be 432. And finally, we need that because we need the standard deviation of x plus x plus x. And the square root of 432 comes out to be 20.8. So hopefully you're feeling pretty good about this now, because we have two little word problems that we're going to do that use the exact same concept. So let's look at the first word problem. A company selling vegetable seeds in packets of 20 estimates that the mean number of seeds that will actually grow is 18. So we just got a data value. We found out that the mean is 18. So I'm going to jot down some notes. That means E of x is 18. With a standard deviation of 1.2 seeds. So the standard deviation of x is 1.2 seeds. And so one thing we need to find automatically is the variance of x. So if you remember, we take standard deviation and we square it. What's 1.2 squared? Well, I get 1.44. So here's kind of all my important data. We are buying 5 different seed packets. We want to know how many bad seeds do you expect to get. So our focus is bad seeds. Okay, so we're simply going to find the expected value of, we have 5 packets, so we need 5 x's. But notice we are asking for how many bad seeds. Well, if there are 18 seeds that grow, that means there are 2 bad seeds. So the expected value is going to be, if we use our formulas that we were just using, this is formula 3. We're going to take 5 times the expected value of x. And so the expected value for bad seeds is 5 times 2. On average, we get 2 bad seeds in each packet. So that's an average of 10 bad seeds altogether. Expected value. So we need to find the variance now. What's the standard deviation? We need to first find the variance in order to find standard deviation. Now, let's take a look at how we're going to do this. So we need the variance of 1x and another x and another x and another x and another x, because we got 5 packets. So with variance, if we have 5 x's, we just do the variance 5 times. Well, what would happen if could we write this any simpler instead of writing this out 5 times? Because I'm out of space, and I know you are too. Well, each one of these variances, if we come up here and we look, is 144. 144 plus 144 plus 144 plus 144 plus 144. Well, is there an easier way of writing that? Absolutely. We could just take 5 times 144. And we would get a variance of 7.2. So if we have to add over and over and over again, we can just multiply by the whole number to figure out the answer quicker. But this question was asking for standard deviation, so I need to find the standard deviation, I need to square root 7.2, and the square root of 7.2 is 2.7. Now, we did make one assumption about the seeds, and do we think that that assumption is warranted? One thing that must be true here, if you remember, we can't have one packet of seeds affecting the other packet of seeds. That's what it means to be independent. So we must assume each seed packet is independent of the rest. So that's one huge assumption we have to make, and absolutely, yes, it is safe to assume that seeds don't affect each other. So let's look at the very last example. Owners of a televised fundraiser know from past experience that most people donate small amounts, $10 to $25. Some do donate larger amounts of $50 to $100, and a few people will make very generous donations of $250, $500, or even more than that. Historically, pledges average, here's some info, average about $32 with a standard deviation of 54. So we know the average, we know E is 32, and we know the standard deviation is 54. What we don't know is the variance. So we're going to quickly take 54 and we're going to square it, and we get 2916. So we have 120 people call in pledges. What are the mean and the standard deviation of the total amount raised? So let's start with the mean. So we need the expected value of 120 people calling in. So 120 X's. Well, as we already know, that's simply 120 times the average or the expected value per caller. So 120 times 32 is a good amount of money raised. It looks like 120 times 32 is $3,840. Now, if you remember from the previous example, with variance, we don't want to write out 120 X's. That's crazy. So we know it's X plus X a whole bunch of 120 times. So we talked about the easy way on the last example is simply take 120 times the variance of X. So we're going to take 120 times 2,916. And yes, you should get a very, very large number. I got 349,920, very large. And the standard deviation of all those X's, the square root of 349,920 is $, 2 decimals, 591.54. And again, what assumption did we make? Each person donating is independent. Whoops, I can't spell. Is independent of others. And that's the end of today's lesson.